Hello friends, welcome back to Rising Mathematics. In this video, we are going to solve this question from linear algebra based on the concept of linearly independent vectors. Question is, let x1, x2 up to xr be non-zero elements of vector space Rn and assume that xj dot xk is 0 for each j not equals to k. Show that these elements x1, x2 up to xr are linearly independent vectors of vector space Rn. Now, in order to prove this given result, firstly, we need to recall concept of linearly independent and dependent vectors. So, let V over field F is a vector space. The vectors v1, v2 up to vn in vector space V are said to be linearly dependent over field F if there exist scalars say a1, a2 up to an in field F, not all of them 0, such that the linear combination a1 v1 plus a2 v2 plus and so on plus an vn is equal to 0. Now, if all the scalars a1, a2 up to an are 0, then vectors v1, v2 up to vn are said to be linearly independent. Now, we are going to use this concept to prove the given result. So, proof. It is given that vectors x1, x2 up to xr are non-zero elements of Rn such that xj dot xk is 0 when j is not equal to k. Now note that j and k will range from 1 to r. Now our claim is to show that vectors x1, x2 up to xr are linearly independent. So for this, consider the linear combination a1 x1 plus a2 x2 plus and so on plus ar xr is equal to 0 and call this expression as star. Then for the vector x1 in Rn, we have, if we take dot product of this x1 with both sides of the expression star, then we have a1 x1 plus a2 x2 plus and so on plus ar xr dot x1 is equal to 0 dot x1. Now in the next step, this 0 dot x1 will be 0 vector, and using properties of dot product, RHS can be written as a1 x1 dot x1 plus a2 x2 dot x1 plus and so on plus ar xr dot x1. Now note that from the given condition, this x2 dot x1 will be 0 as 2 is not equal to 1. Then next term will be x3 dot x1 and that will be 0 since 3 is not equal to 1. Similarly, last term xr dot x1 will be 0 as r is not equal to 1. So, all this term will be 0 and we get this. And therefore, we have a1 x1 dot x1 is equal to 0. Now note that x1 dot x1 is not equal to 0 as 1 is equal to 1. So, we get the scalar a1 must be equal to 0. Now, consider the vector x2 in Rn. Then if we take dot product of this x2 on both sides of star, we get this expression. So, 0 dot x2 will be 0 vector and LHS becomes a1 x1 dot x2 plus a2 x2 dot x2 plus and so on plus ar xr dot x2. Now again using given conditions, x1 dot x2 will be 0 as 1 is not equal to 2. Similarly, xr dot x2 will be 0 as r is not equal to 2. So we will get a2 x2 dot x2 is equal to 0. Now x2 dot x2 will not equal to 0 as 2 is equal to 2. So we must have a2 equals to 0. Now if we continue this process, after taking the dot product of expression star with a3, a4 up to ar, we will get a3 equals to 0, a4 equals to 0, similarly ar equals to 0 respectively. Now as all the coefficients a1, a2 up to ar comes out to be 0, and we have considered that this linear combination is equal to 0. So this will be the trivial representation of 0 vector in Rn, and thus using the concept of linearly independent vectors, the vectors x1, x2 up to xr will be linearly independent vectors in vector space Rn, and this proves the given result.